Okay, so let's get going. So what we're going to talk about today is the upcoming release of MASTA, which is MASTA 11. My name is Sam Webster. I'm Senior Technical Trainer here at SMT. I think I know a lot of you already. And this webinar is going to be around about 1 hour long. I'm going to go through some of the major developments in MASTA 11. As always with the MASTA releases, there are a lot of smaller things that go on in the background as well, smaller tweaks, smaller additions, which I'll touch on a few of those and point you to where you can find more information on those as well. But I'll be focusing on the major developments. So the first thing to mention is the release date for MASTA 11. So there isn't a fixed release date as of yet, but the MASTA 11 first release should be coming in the next few weeks, so in the coming weeks, obviously dependent on ironing out any remaining bugs and finishing off bits of functionality. As I'm sure you're all aware, with software development, it can be somewhat flexible just during the development process. So another thing to mention is licensing for MASTA 11. So some of the features I show you today are licensed under separate licenses. Obviously, we can give you information on that if you require. Some of the bits of functionality I'll be showing you will be included in the core modules, or maybe modules that you've already got available to you. So just be aware of that as well. Now, of course, in this 1 hour overview, there's only so much I'm going to be able to show you. So there will be a lot of more detailed tutorial video content kind of information as well. So I think most of you are familiar that we have that content, and you can access it in a number of different ways. So the main way of accessing it is by logging onto the Smt Portal, the support portal, and you can access all the links to our tutorial videos through there. And as of MASTA 11, and maybe the latest release of MASTA 10, you can also get to those links through MASTA's internal help file as well. So you can get to the links for those tutorial videos. So let's get started. The first thing I want to show you is some of the changes that have been made to the modeling process in MASTA 11. Now, so hopefully you can all see my screen being updated. So what I want to draw your attention to is obviously MASTA 11 interface is very, very similar to what we've seen in previous versions. But if you're in the 2D view on your design mode, you'll notice that there's this extra tab down here, which we're calling the component palette. And this is essentially there to allow you to rapidly develop your MASTA models, particularly good for concept modeling and manual modeling, that kind of thing. And what it basically allows you to do is, instead of going through the whole process of right-clicking, adding an assembly, adding components, which you can still do, you can just click on the item on here, and it will add that to your MASTA model. And it doesn't just stop there. You can also, it's kind of like a click and drag and drop kind of process on here as well. So if I sort of select on this bearing here, I can just click and drag that bearing onto the shaft I've already got on the main 2D window. It will automatically connect those two components together, and it will position that component where I dropped it as well. And what this basically means is that you can start to build up a very complex model fairly quickly. So for example, if I just want to make a very simple but complete concept model, I can just start dragging components onto existing components. You can see it being constructed in the 3D view over on the right-hand side. I'll show you about moving those in a second. So you see there, we technically have a completed MASTA model at this point, and that took me a matter of seconds instead of maybe 2 or 3 minutes that it would take the experienced MASTA user using the old modeling methodology. Another thing that we've improved upon here is the way that you access some other model building functionality and key key actions in the modeling process. So for example, moving components, manually connecting components, that kind of thing. You might notice that they've been removed from the menu bar on the top right of your screen, but not to worry, they are easier to access at this point. So if I select a component in my 2D view and then just right click anywhere on that component, you then get access to this new radial menu. And this gives you immediate access to all of those essential commands. So things like connecting components, moving components, duplicating components. And if you're on a shaft, you can use it to edit the shaft profile as well. That's how you get to the edit shaft profile tool. So for example, if I wanted to move this whole assembly here, I could select all of those components, right click and move. And it's really easy to just move that all around. Now, obviously, this is a really simple demonstration here, but you can build up very complex concept models using this functionality. I should say as well that if there is any questions as we go along, please do feel free to ask them. I'll probably answer those questions at the end of the webinar, but yeah, just ask them as you're going in. You should be able to find a questions tab over on the right-hand side of your GoToWebinar screen. Okay, so the next thing I want to show you is what we're calling the CAD Link. And this is going to be split out into a number of different sections. Some of you might be familiar with this to some extent from the technical seminar that we went through late on last year. Hopefully I'll build on that, and people who weren't present for the previous one will get some useful information from this as well. Basically, it allows us to link our MASTA versions, our MASTA windows, to a Spaceclaim instance. Now, hopefully everyone's familiar with Spaceclaim. It is a CAD package which is owned by ANSYS, and we've developed the CAD Link to work very, very closely with Spaceclaim, and it really does build on the capabilities of the MASTA modeling process in terms of ease of building the models and ease of optimization, ease of analysis. It really does simplify the whole process. There is a few things in here as well if you don't have Spaceclaim, but the main benefits are achieved with Spaceclaim. And we can highly recommend Spaceclaim as a software package as well. So if I just rearrange my screen, if you bear with me for 1 second. So the first thing I want to show you is what we're calling the active 3D modeling. So this is where you can actually construct your MASTA components, so shafts, bearing, gears, whatever else, actually directly from a 3D CAD model, rather than having to manually create it or using the 2D CAD modeling process that a lot of you might be familiar with. So just to show you what I meant by the 2D CAD modeling. So it was this icon up here on your 2D modeling windows where you can actually access this entry here. You put in a DWG or a DXF in the background, and then you can construct your MASTA model using that as an interactive template. So this uses the same kind of functionality, but it takes it one step further. So what we've essentially done is linked our MASTA instance to this open instance of Spaceclaim here. And what we get when we've set all this up, obviously there's a bit more in terms of setting it up, is this MASTA tab within Spaceclaim, which allows us to actually send data from one to the other. So for example, if I want to create a couple of components here, so if you don't use Spaceclaim as your main CAD modeling, of course, that doesn't matter. Spaceclaim is fantastic at opening CAD models from other software packages, so SolidWorks, CATIA, or if you save it as a step file or something like that, Spaceclaim can open them all. So it's really easy to utilize it for that. So what I've got is my internals of my particular gearbox here. And using the MASTA tab, I'm going to say I want to add a component to my MASTA model. And I'm going to start off with this shaft here. So first I need to actually define the components, or the extent of the components. Should be able to see that getting selected in the MASTA window as we are doing this. So you'll see that instant selection in the Spaceclaim window will give you results in the MASTA window. You can then add that in using MASTA. I've not got too much space to demonstrate this, but you can see the 3D model being constructed. I then go over to define shaft profile, and I can just click on the geometry within Spaceclaim, and you can see it being transferred over to our MASTA model as well. And of course, I could do the inner profile as well, but I'll leave that for the moment to save a bit of time. And of course, it doesn't just limit to shafts. You can add all types of components to the model using this methodology. So if I go back to our add component section here, say that I want to add a cylindrical gear in my case, it tells you, as always, what it needs to actually be able to add this component type, the same as it did in the 2D CAD modeling. I can specify some gear set geometry down here, so number of teeth, module, whatever else it might be. And when I have, click on the add button and it brings it into my MASTA model. Now, of course, I haven't defined the geometry in this case, but you can see what I'm getting at here. And then we can carry on. So I'll just add one more component just to show you. So again, I want to add another cylindrical gear. This time it's going to be my meshing gear. You can see the associated lines are selected, and I can add that in as well. So another thing to note here is that the components are being added in the same location in 3D space as they were in the Spaceclaim model. That's because obviously we're using this geometry over here to create the reference geometry within MASTA. Now that might sound like quite an arbitrary, simple thing, but when you come to adding FE components and generating FE components, that is really, really powerful and really effective bit of functionality to have. Okay, so I'm going to jump forward to the next part of the CAD link, which is something we're calling active geometry exchange. So I'm going to just, again, rearrange my screen ever so slightly. And change the model I'm using. So what we've got here is a very simple version of the EV model that a lot of you will be familiar with. We use this one quite a bit for trainings and demonstrations just because it's nice and simple. And what I've got over on the left-hand side is a housing component. Now, in this case, it's been somewhat simplified, it's been defeatured, and it's all just been converted to one component. But you can have more complex configurations in there as well. And what I want to show you here is how easy it is to transfer this data over to our MASTA model for inclusion as an FE component. Now, previously, this was a little bit more work, as I'm sure a lot of you are familiar with. So you would have to utilize some sort of intermediary FE package. You would send the CAD geometry to the FE package, create a mesh, define materials and all that sort of stuff, and then create another file which you then take to MASTA. So it was a fairly streamlined process, but there was a number of steps to it. What we've got now is the ability to just send this geometry directly to MASTA as an STL CAD file, basically. And then once it's in MASTA, we have the ability to actually generate a mesh within MASTA itself, connect it up to all of our MASTA components, and reduce it really, really quickly. So all I'm going to do here is I'm going to say, select on the geometry I want to send over, click on this Send Geometry or Ansys Mesh icon, and you'll see that comes up with a command within my MASTA window, which is actually saying, do you want to create a new FE component in relation to this geometry? I say yes. It creates my FE component. And then I go to my FE mode. And what we have in our MASTA model at this stage is an STL file. So this currently is not meshed, it is just geometry files. But you'll notice this is one of the benefits of being able to create your model in the correct coordinate system. Because my housing was also created in the same coordinate system, it's already in exactly the right place. I don't need to mess around with repositioning it, realigning it. Nice and easy. Okay. And then what I want to show you in here is the ability to actually generate the mesh that will turn this into a MASTA FE component within MASTA itself. So there's a few options here. I won't go through them, just controlling sort of element size, element shape. Sorry, my remote desktop has just minimized itself. Yep, element size, element shape, growth rate. Kind of, it's obviously not the most complex capabilities in terms of meshing. Obviously, you get much more powerful meshing capabilities in a dedicated FE package. But in terms of what you're going to do here for creating stiffness matrices and that kind of thing, it's a powerful little tool. So if I just hit this mesh volume, you'll see it's generated an FE mesh for me there. And then at this stage, I'm at exactly the same place I would be if I'd imported this as a CDB from Ansys or an input file. So I can just connect it really easily to my MASTA components. So you can see there it's got the links to my MASTA components. I could then go ahead and reduce that. So it'll take a little bit of messing around with the settings, but I could reduce that fairly easily and get some results out of it really quickly. There's also kind of a link going on, an active link between MASTA and Spaceclaim here. So let's say I'd made some modifications to my CAD geometry within Spaceclaim itself. I could just hit this reread mesh from Spaceclaim button, and it would actually just update the geometry in my MASTA model with a new STL version of whatever was in Spaceclaim. So really easy to transfer things from one to the other. Okay, so what you also have the ability to do within here is to do a mesh exchange as well. So the same kind of method as you would exchange the CAD geometry, you can actually use Spaceclaim's meshing capabilities. Now, I'm not going to go through this in a lot of detail. I just want to very briefly show you. So here is a gear blank, for example, which we've actually used Spaceclaim's meshing capabilities to actually create the mesh for. And then we would be able to transfer that in exactly the same way. So I could just select the geometry, send it over to to MASTA, and it would actually bring it in as an already meshed component. So it would already be ready for connecting to our MASTA models. Okay, and then another thing we have in here is something called active parameters. So this is a really powerful bit of functionality, which actually allows you to bring in MASTA's optimization capabilities to external CAD components. So rather than just being able to optimize gears or assembly layout or shaft parameters or whatever it is, you can actually use MASTA to perform detailed studies or optimization processes on externally generated components like this gear blank here. Now, granted, this is very, very simple. I'm just using it for demonstration purposes. But what I want to do to show you this, I'm going to send this over in exactly the same way as in send the geometry over. But within Spaceclaim itself, what I've actually done is defined a few parameters here. So for example, I've specifically defined the number of holes in my gear blank. I've specifically defined some of the thickness parameters of parts of my gear blank and various other things as well. So the hole size, for example. Now, if I go ahead and send that over the same way to my MASTA model and just connect it to whatever I'm replacing, again, it's a really simple, really quick process. And can again be meshed really easily. But what you'll notice is that as well as the mesh information here, which we should be able to see, we've also had those dimensions imported into our MASTA model. So those parameters that we saved over in Spaceclaim have now been imported into our MASTA model as well, and I can control them from MASTA. So let's say, for example, I want to change this design. I want far fewer holes. I want the holes to be a different size. I want the thickness of the blank to be a lot lower. Once I've applied my changes, I say reread from Spaceclaim. It will then send commands to Spaceclaim to actually change that geometry for us, to actually change those parameters, and it will resend that information over to MASTA. Now, this might seem fairly arbitrary at the moment, but it also means that we can combine, because we have those bits of information within MASTA, we can actually use that in our optimization tools. So things like Runner or things like the parametric study tool, we can include those parameters in there so we can actually do a defined study of what impact the number of holes will have on certain parts of our analysis, or what impact the blank thickness will have on our analysis. So this is an incredibly powerful tool which opens up a lot of capabilities for people who are doing these kind of studies. And it's not just on shaft components. You can obviously do this on bits of your housing as well. So let's say housing wall thicknesses or the size of bearing supports or that kind of thing. You can do all this stuff. Whatever you can create a parameter of, you can run that within MASTA as well. Okay, so that should give us a nice little overview there of the CAD Link. Obviously, that is a very quick overview, but the capabilities of what you can do with that are so powerful. So what I want to show you next, and one of the other big additions to MASTA 11, is the ability to actually model cycloidal drives or cycloidal systems. So we've got a couple of example models which have been added to MASTA 11, which you'll all be able to access when you get this, which is, where is it? In components, cycloidal drives, and we have the ability to do both RV cycloidal and simple cycloidal systems. I've already got those open somewhere. like this. So cycloidal drives are normally used in sort of robotic applications or maybe heavy industry applications. They've got incredibly large ratios, and they're very good for sort of precise positioning of components. They are being used more and more in sort of automotive applications and other fields as well. So we've decided to sort of include this. As I've mentioned, there's two different types of configuration you can model. So this is the simple cycloidal setup, and we also have the RV cycloidal setup. And as you would expect from MASTA, you do have the ability to incorporate this into the entire system model. So it's not just a case of modeling the cycloidal disks on their own and doing a bit of analysis on them. You include it as part of the entire system model within MASTA, and then that will have an impact on the deflection of other components, the loading of other components, and everything you would expect from any sort of model within MASTA. So if I just take a look at those in PowerFlow just to show you. You can see those in operation, for example. If I move forward to system deflection, again, you can kind of see how that's being incorporated into our system model. So you can see all the forces, you can see the deflections on those particular components. If I hide those components, we should be able to see the loading on the different pins. And within here, we do have a cycloidal strip loads chart as well. So just an extra bit of functionality which allows us to see the actual loading on the different pins. And then we get the same kind of abilities for the advanced system deflection as well. So I think most of you are probably familiar with advanced system deflection and what it does. It's a quasi-static analysis, basically looking at your system in rotation. So numerous system deflection studies, one after the other, as it rotates slightly. So we can see how the loading changes and how the performance of the system changes as it's going through its rotational cycle. And as you would expect, we can include the cycloidal drives in this configuration. I don't know how well that graphic is transferring over a remote desktop. Hopefully it shows fairly reasonably. Okay, so the next thing I want to show you is asymmetric gears. So this is another one of the major additions to MASTA 11. There's a lot of work gone into incorporating this functionality. And I have another model here which I'll use for the next couple of things. So this is a more complete version of our EV that we were just looking at. And if I hop over to the gear macro geometry mode, one of my designs is just an asymmetric one. And if I just zoom in on that, hopefully you can see, it's not the most dramatic, but you can see that there's a different pressure angle on the different flanks of the gear. So again, this is something that's been used in certain industries for many years. So aerospace has been used for quite a few years, but I think it's becoming more and more commonplace in automotive and various other industries as well, to be able to do a different pressure angle on the different flanks, purely because you want to be able to account for the different loading expected by each of the different flanks. Now, the actual specification of this is really, really simple. So on your default gear editor, you'll see there's a new entry in here, which is asymmetric. And by clicking on that, you get, it's messed up there, but you do get the ability to just input different normal pressure angles for each of the individual gear flanks. It will also allow you to have separate inputs for certain parameters to do with the root of the gear as well, which is what's messed it up in this case. So the edge radius factor, for example, or the edge radius, will now be separated into left and right flanks. And if you specify that fully, you do get something like this, which allows you to have those different pressure angles on the different flanks. Now, asymmetric gears don't really have as much research into them as symmetric gears. So in terms of that, we haven't applied any particular rating standards for them, probably because they don't exist. But we do have the ability to incorporate these designs, so asymmetric designs, in our LTCA calculations. So our basic and advanced LTCA studies, we can incorporate the asymmetric gear design into those analyses. So if I go to my microgeometry mode, and hopefully I've not lost my setup here whilst messing around with other options. So I'm basically running my asymmetric design. I've got some basic microgeometry on there, and I'm running that through using advanced LTCA. And it means that you can get very detailed results on the different flanks. So you can see the contact pattern distribution, you can calculate the transmission error in those different loading conditions, same as you could previously, but now applied to those asymmetric gear designs. Okay, so the last of the major changes, the major new bits of functionality I want to show you is something that we're calling Atsam, so ATSAM, which is Advanced Time Stepping Analysis for Modulation. Now bear with me while I just get my model ready. Okay, so this has been included. It's an extension of MVH analysis, really. So it's a new mode, it's a new module, but it's MVH capabilities sort of added onto. And what it basically allows us to do is to look at the effects of modulation of different components and how that might affect the MVH behavior. So better to show you by demonstration rather than just explaining it here. So as an example, we've got a gear blank in our model here, which is pretty extreme, but does show the behavior of this quite well. So we see we've got two massive cutouts in our gear blank here. So as we actually rotate through this system, we would expect some kind of modulation because the stiffness of the component is going to change dependent on where the engagement with the engaged gears are. As a result, the transfer path will change, the natural frequencies might change somewhat, and it will change the MVH behavior. Now, in the normal MVH mode that we have, now obviously that's a very powerful tool for doing the MVH analysis, but the sort of static nature of that analysis and the fact that we're linearizing around a certain model means that you can't capture all this complex behavior if you are expecting some kind of modulation. And this is where Atsam comes in. So I'm going to start off by showing you the results of or the setup of the Atsam. So what we're basically doing, so in this particular study that I've set up, we're going to be showing the excitation using basic LTCA. So the actual transmission error of the system will be calculated using basic LTCA in this case, but you can use advanced LTCA. You can use advanced LTCA using advanced system deflection, and you can use the fairly recently introduced advanced system deflection current load case setup. So there's various levels of detail you can use to calculate transmission error, whether it be static transmission error, as it is from basic and advanced LTCA, to a more robust, more hesitate to say dynamic, I think, but you can get a more detailed representation of the transmission error through something like the advanced system deflection current load case setup. So when we're actually using the normal MVH mode, we're seeing the dynamic response of the static transmission error at a fixed position relative to the holes in that gear blank. So basically, we're looking at the analysis of a static value of transmission error, and we're looking at it in a static position or a static rotational position of that gear blank we have in there as well. What we're doing in Atsam, and if we are using basic LTCA, is we are seeing the static TE applied to a sequence of MVH models at the different rotational positions. So what that basically means is that we're recalculating this process as we're going through the rotation of that particular gearbox, and we can see what happens. We can see how the behavior changes as gearbox rotates, and it will allow us to get that modulation behavior, that sort of sideband split as well. And that sideband split is due to the change in the transfer path at those different positions during that rotational cycle. So the setup is fairly easy. It will use your MVH setup wherever possible. So in terms of what you're using as harmonic excitation type, the magnitude of the number of modes, that kind of thing. And then you specify more information in terms of what kind of magnitude of rotation of components you want to cover. So is it the full rotation of a gear blank, for example, that you want to address? How many steps you want to cover this in? Various different settings, which I won't go through them all now. It is fairly easy to set up though. And then the results you'll see from this, the actual plots that are available are going to be very, very similar to those you've seen in MVH mode, but they'll obviously have that additional bit of information. So just to demonstrate this to you, I'm going to go to my MVH mode to begin with and just show you our 3D models, just as a reminder. So we've got a very simple model. We're looking at the excitation generated by the first gear set here, which is this gear set from the motor to the gear blank that we've replaced. This is the excitation we're actually going to be looking at. If I look at the excitation on a bearing, go to my dynamic response, and this is what a lot of you who utilize the MVH capabilities will be used to seeing. So you'll see one order line for each harmonic of the excitation we're looking at. So you can see that's my first harmonic, that's my second harmonic, and this is what we would expect to see from the frequency domain analysis that we're doing in our normal MVH study. So it's very effective in a lot of cases, but in terms of looking for modulation, it's not quite detailed enough. So by upgrading this to the Atsam simulation, and if I look at the same plot, we can see there that we've got a lot more detail. Now, obviously, it doesn't generate that quickly. I'll say now, there's simulation I did in the background there. It does take longer to calculate because it's getting more information. It is still very fast, of course, compared to other methods, but be aware that it does take a little bit longer. And what you can see there is we're looking at exactly the same situation, but because we've looked at the entire rotation of that gear blank, And we're now capturing that modulation information. We can see how the modulation has affected that response and how the sidebands have been produced. Now, obviously, there's a lot more technical information goes on in the background of this, which I won't be going on to today, but we do have some information available if you wish. So please let us know if you want a bit more information on this. Of course, you can get in contact with us. Now, that's the main bits of functionality. That's the main features I wanted to show you. Of course, as I mentioned earlier on, there are a lot more things that are included in Master 11 than what I've shown you there. It's not been released yet, of course, but with the actual release of Master 11, whenever that is in the coming weeks, you will have access to the release notes document and the accompanying tutorial video, which will release alongside it, which will give you more information on all of these little tweaks, smaller additions that have been made alongside these major ones which we've demonstrated today. So, for example, just to talk to you through a couple of these, I won't show anything on the screen particularly. So we have the inclusion of additional standards for micropitting and for scuffing. They've been included in Master 11. So the ISO technical standard 6336 22, part 22, 2018 for micropitting, and some others for scuffing. So they've now been incorporated into the software and can be used by all of our users in Master 11 or with necessary licenses. Also in there, there's a lot of work gone into script forward compatibility. Now, this is an issue which has come up a few times for various users, and it's something we've been keenly aware of. There's a lot of work gone into actually making sure your scripts are able to be forward and backward compatible. So when changes are made to the API, when new things are added, and I'm sure there's other nuances in there as well, we want to make sure that obviously you don't have to repair your script. You don't want to have to rewrite part of it in order to get it to work again. So the scripts have been made so they're much more compatible with older and newer versions. There's also the inclusion of a faster solver within Master 11 as well. So with the solver, I'm referring to the imported FE. You can choose the type of solver that you are utilizing here. So the solver will be about 20 to 30% faster for people who use in-core calculations. So if you're one of the lucky people that has quite a lot of RAM memory in your PC, you'll be able to actually get a 20 to 30% increase in calculation time, which if you're doing quite a large component reduction can be a sizable chunk of time. However, the greatest benefit comes to those that are having to do out-of-core calculations. So if you don't have as much RAM memory and you're doing quite a large model reduction, you might have to use out-of-core solvers, which do take a lot more time because it stores the information on your disk. And if you are using an SSD and you're using an out-of-core solver, then you can see a 4 to 5 time increase in the speed of the reduction time. So if you are using that methodology, is a massive increase in the calculation time. Okay, so there's a lot of changes there. There's countless more as well. I'm looking at the release note documents as I speak, and there's probably at least 15 other major headings in there which I've not had time to go through at this point, but we'll get that information over to you when it's applicable to do so. So just keeping an eye on the time. So that is the major content I wanted to show you. If you just give me a couple of minutes just to take a look through some of the questions that have come in, I'll see if there's any I can answer now. If I can't answer them right now, I'll be sure to, or don't have time to get to them, I'll be sure to address those after the webinar as well. So give me 1 or 2 minutes just to take a look through, and I'll be right back with you. Okay, so one of the questions that came in was, I think there's quite a lot to do with the CAD Link capabilities. So I'll try and pick through a few of those. So does the CAD have to be a step, or can it be native Creo CAD? So it doesn't have to be a step file if you're importing it into Spaceclaim. So obviously a lot of this relies on Spaceclaim, because that's what our link is primarily with. But you can open files from those other CAD packages in Spaceclaim fairly effectively. So we don't have all the CAD packages. My main experience is with Spaceclaim itself, when with SolidWorks, but I've noticed that you can import SolidWorks files, step files, various other file formats into Spaceclaim itself, and it will read those fairly effectively, or very effectively, and will create the model for you. So I would not think that Creo is any different. I think you can do the same with that. And then kind of in that same vein, there's a question which says, does the CAD Link work with other CAD softwares? So NX, CATIA, Inventor, that kind of thing. So again, just to reiterate, the main link is to do with Spaceclaim, but you can open the geometry from the other software packages in Spaceclaim. Something I actually missed, which I did want to show you. So there is some ability to still utilize that kind of functionality without having that Spaceclaim license. And it's to do with importing an STL file directly. So hopefully you can still see my screen. I think you can. Okay, so what I've got in my little file structure that I've been using here is an STL file. And these STLs are fairly generic geometry formats. You can just save those from most CAD packages, all of the ones I'm aware of anyway. You can save them from Spaceclaim, SolidWorks, Creo, whatever else. And the STL is generally what will be created when we transfer from Spaceclaim anyway. But we can import the STL file directly into MASTA, as well as having that link with Spaceclaim. So I've created a new design for my housing here. And on the import and export tab, the same place where we would normally import FE external files, so whether you've created an externally reduced file or a full FE mesh, you can also now import an STL mesh. If I read an STL file, we're basically at the same stage there. So we can now create the mesh of that component using the STL file as a guide and create an FE component from that can be used in our master model. Now, of course, you do lose some of the capabilities here. So you won't be able to automatically reread the geometry. You won't be able to utilize the parameters that I showed you earlier on, but it does give you that route to not having to use the intermediary FE functionality, the intermediary FE package. So I've imported the STL file there. I could just go straight through to my meshing and create the mesh. I've just chosen this at random, so hopefully it's successful. And there we go. So we can create the mesh and then again, immediately connect that to our master model. Okay, so there's a question coming as well to do with, is there a plan to write a paper or an article on the new modulation feature? I don't know 100%, but I think it is in the pipeline, yes. As to when exactly that is, I will get back to that. I'll get back to you with that after the webinar once I've spoken to the necessary people. Okay, so there's another one saying, will it do a webbed disk with holes? Hopefully, I think that was probably asked before I imported the gear blank, so hopefully that one's been answered. But yeah, any geometry that you have within Spaceclaim or within your STL file, you'll be able to import that. Okay, and then there's another question there, which is, can you give us a list of modules of Spaceclaim that would be needed? I was trying to find out the information for Spaceclaim itself and what you would need within Spaceclaim. I don't think you need much more than just a basic license, to be honest, to actually use this functionality in Spaceclaim. If you want to use the actual Spaceclaim meshing, I think that's a bit of an extra license on their end. But if you want to actually just transfer the geometry to MASTA and then mesh within MASTA, I think that transfer is fairly, you only need your basic license. And in terms of the licenses within MASTA that you would need to do this, of course, that information will be available upon the release of MASTA 11. So, and then again, just to reiterate, there's another one that's come in asking about the release of MASTA 11. So it's not released as of yet. We are still doing some final tweaks, some final additions, final tests. It should be released in the coming weeks, but development cycles can obviously change slightly based on workload. But yeah, in the coming weeks, we should have the MASTA 11 release out. Unfortunately, I can't give you an exact date, so hopefully that's okay. Okay, so there's another one asking, can we add a lumped mass in the FE mesh created within MASTA? So hopefully I'm understanding the context of the question correctly, so I apologize if not. But you can connect any component to anything that you actually mesh within MASTA itself. It will be considered exactly the same as other FE components that you import into your MASTA model. So for example, I could create condensation nodes on here. I could attach additional components to it, so you can position them in 3D space and connect it to a condensation node, and it will consider that to be a connected lumped mass. Or you can connect things to a shaft you've imported. If you were able to do it using the previous FE functionality, so if you're actually importing the mesh information, you'll be able to do it using the new meshing capabilities as well. So you can connect external MASTA components to the FE components. Okay, and there's a question saying, does the mesh rely on the STL surfaces? I believe it does. That is a question I will refer to the appropriate people and get back to a little later on. But yes, I believe it does rely on those surfaces. Okay, there's one that says, how do you manage bolted connections in imported FE from Spaceclaim? So what you're actually doing from Spaceclaim, or if you're creating an external STL file to import into MASTA, is you are just importing that geometry. So as you would with other bits of FE, or maybe not, you could define the grounding points, whether it be an RB2 or RB3 connection, within MASTA itself, the same as you would with your previous FE instances. So for example, with my housing I have here, I just imported and meshed a geometry file. So there's no grounding information or bolted points or anything like that. but I can use the tools available within MASTA to actually create those for me. So for example, if I wanted to just ground this entire surface, I know that's quite arbitrary, but just to demonstrate, I could say I want to select that surface and ground it. That will create rigid connections at that surface. Alternatively, if I wanted to create flexible mounting points, so let's say I want to create a flexible mounting point here, for example, I could say select the surface, create a condensation node, and then I could create a distributing, so RBE3 or kinematic RBE2 connection with a component attached. So let's say a shaft hub connection, for example. That will create a component attached to that condensation node, which I then have control of that stiffness. Okay, so the last question I'll answer, because I know we're short on time, and apologies if I've missed anyone else out, I'll reply a bit later on, is whether or not the creation of remote points and condensation nodes are recommended in ANSYS. So to be honest, I would recommend making the condensation nodes in MASTA anyway. I've not used the creation of remote points in ANSYS for quite a few years, but when I did use it, I found that it was fairly difficult to make sure that the condensation nodes were in exactly the right place, connected to exactly the right surface. And actually connecting it to your master model was fairly difficult. Actually creating them within MASTA, so you've seen me create a fairly simple condensation node here, but if I wanted to actually create them connected to my master model, if I just so you can see there, for example, to create these condensation nodes which connected to all these master components was just a click of one button, and then you can separately define what search region it's looking for to attach to the FE component. My recommendation, if it's available to you, would be to create the condensation nodes within MASTA rather than having to define them in ANSYS, just because it's much, much easier. Okay, so apologies if I didn't get to your particular question. I will answer them after the webinar. I'll reply via message or email or something. I hope this has been useful to everybody. And we've gone through all the major things for Master 11. If you have any additional questions, please feel free to message the normal channels. So you can message support or sales at smartmt.com, and we'll be happy to answer those. As I say, Master 11 will be released in the next few weeks, hopefully, bar any major issues. Yeah, so we hope you've enjoyed the webinar, and we'll speak to you next time.